Welcome back. I know you couldn't stay away from me. Day 4, section 5.5. We're going to continue on our journey of finding derivatives. So today we're looking at second derivative and my favorite, implicit logarithmic differentiation. So what are we going to look at? We've already talked about derivatives and natural logs, so we're going to throw them into our second derivative now. So how do we find the second derivative? Well, the first thing we're going to do is find, the first derivative. Our first derivative here, we have a chain rule since we have a quantity to an exponent. So we have 3 natural logs of x, decrease the exponent by 1, we get squared. And then derivative of the natural log of x is 1 over x. I can rewrite this if you wish, if we want. So it makes it look a little nicer. We have 3 natural logs of x squared. That doesn't look any different. But then we can put this all over that x. And that allows us then to find the second derivative here of this function because we have now a quotient rule. So our quotient rule is going to give us x and then derivative. Well, that 3 is just going to kind of hang out there. Natural log of x to the second. I guess I could make the 3 a 6, couldn't I? So we multiply the 2 to the 3, we get 6. Inside stays the same. Decrease your exponent by 1. Times the derivative of that inside, which is 1 over x, minus my numerator, and then times the derivative of the denominator, which is 1, and it's all over my x squared. I'm going to change a marker there, so we're going to clean this up. We have x times 1 over x. Those will cancel for us. So we get 6 natural logs of x minus 3 natural logs of x squared over x squared. Can we do anything with this? Yes, we can make this maybe look a little prettier. I guess if that's a possible thing for this. We could factor out a GCF out of that numerator. It's not going to matter a whole lot. Maybe multiple choice questions somewhere along the line, they would do that to you. So we could have 3 natural logs of x times 2 minus the natural log of x over x squared. If we were finding zeros of this as well, we would probably want to go ahead and factor that out as well. And that gives you our second derivative. I'm going to label that as well if you want. So our second derivative is there. Another second derivative here, we have x to the third natural logs of x. So first derivative here, we have x to the third natural log of x. We have x to the third times 1 over x, derivative natural log of x. To that we're going to add the natural log of x. Derivative of x to the third is 3x squared. I'm going to go ahead and clean this up just a little bit before we go into our second derivative. So we get x squared plus, I'm going to go ahead and write this as 3x squared natural log of x. Just kind of looks a little nicer to work with. So to find our second derivative, we know the derivative of x squared, that's going to be 2x. Derivative of 3x squared natural log of x. Since I have x's in both of my terms, I have a product rule. I'm multiplying those two together. So I get 3x squared. Derivative natural log of x is 1 over x. So then we're going to add the natural log of x. Derivative of 3x squared, which is 6x. We're going to go and clean this up just a tad bit. We get 2x plus 3x squared times 1 over x is 3x. And then plus, again, I'm going to bring the 6x to the front of my natural log of x. I'm going to combine my 2x and my 3x to get 5x plus 6x natural log of x. And again, we could possibly factor out that x. It's only going to be useful if we go to find our zeros, our critical points, and that such like. So, points of inflection, I guess, for second derivative. So we have x times 5 plus 6 natural logs of x. And that's our second derivative, nice and clean. Now to the fun stuff. Yes. Logarithmic implicit differentiation. Oh my. Remember implicit differentiation? That was when we had maybe x squared plus y squared equals 16. That was my favorite example that I always used. So we found the derivative, and we got 2x plus 2y dy dx. We took the derivative of y equals 0, and we solved for dy dx. So you look at this and you think, well, I don't have any y's in this part. Why would I use implicit differentiation? Well, recall f of x means y, doesn't it? So if I were to find the derivative of this function here, notice I've got this function times this function times this function. So I'd have a product rule within a product rule. That would be nightmarish if you would even want to think about finding the derivative in that form. So what I like to do, and what we like to do in calculus, is to take the natural log of both sides. So if I take the natural log of the left side, and I can take the natural log of the right side. And we can do this because we've done the same thing to both sides of the equation, haven't we? All right. Well, what does that allow us to do? That's going to allow me to break this out and to expand it using my natural log rules and my logarithmic laws. So recall, if I have an exponent, that's going to come to the front of my natural log. And if I have a product, if I'm multiplying things together, that goes to addition. So I'm going to have 2 natural logs of x plus 3 plus 3 natural logs of 2x minus 5 plus 4 natural logs of 3x squared plus 1. I can now go ahead and find the derivative. Natural log of y derivative. That's going to work just like the natural log of x. Remember, natural log of x derivative is 1 over x. Natural log of y is going to be 1 over y. But since I took the derivative of a y, I got to put in that dy dx. Derivative of 2 natural logs of x plus 3. I got my 2, and then multiply it by the derivative of x plus 3 over x plus 3. Remember, natural logs, we take the derivative of the function divided by that function. So it's going to be 1 over x plus 3. Plus my 3 times derivative natural log of 2x minus 5. Derivative 2 over that function 2x minus 5. And then we have 4 times derivative 3x squared plus 1 is 6x over 3x squared plus 1. The fun has just begun. Don't worry. So now I can go ahead and multiply my 2, my 3, and my 4 in. So I get 2 over x plus 3. I get 6 over 2x minus 5. And I get 24x over 3x squared plus 1. I want to go ahead and find, you guessed it, a common denominator for these 3 terms. That common denominator, since they're all different, it's just going to be one massive denominator. Yucky, yuck, yuck, but it's what we have to deal with. So what do we got here? I'm going to make this very large. Hopefully I get it all in one. So the 2 is going to get both of these denominators. And I'm going to go ahead and multiply these 2 together since I know I'm going to do that, and I'm going to run out of some room. So kind of ulterior motives here. So 2x times my 3x squared gives me 6x to the third. 2x times the 1 gives me a 2x, and a negative 15x squared, and then minus 5. My 6 is going to get these 2, so that's going to be a 3x to the third plus x plus 9x squared plus 3. I know I'm going to run out of room. My 24x is going to get these 2, so we get 2x squared. What do? I have 6x and then minus 5x, so that's a plus 1x. I'm just going to write it down here. And then minus a 15. So that's going to be those values there. And again, that's still equal to that 1 over y dy dx. Don't lose that. I'm going to go ahead and distribute my 2, my 6, and my 24x. Oh, good heavens to gracious. So, my 2, I'm going to get a 12x to the third. Again, that's equal to that up there. Plus a 4x minus 30x squared minus 10. Plus 18x to the third. I should write these under these, shouldn't I? I'm going to go ahead and do that. I'm going to move that 18x to the third over here just to make my life easier. Plus 6x, and then 6 and 9 gives me a positive 54x squared, and then plus 18. And here, 24x times 2x, that's going to give me a 48x to the third, plus 24x and x, that's going to be 24x squared, so we'll move that over here. And then 24/15, that's a minus a 360x, isn't it? So I'm going to go ahead and multiply or add those together. So I get 10, 20, I get 30, I get 78 x to the third. 360 minus 10 is going to be 350 x, a negative. Here, what do we got? We got a negative 6 when I add those. So I get a 48, so plus 48x squared, and then plus 8. So that's what that's going to equal all over that denominator of x plus 3, 2x minus 5, and 3x squared plus 1. Again, that's equal to 1 over y dy dx. We're not done yet. Oh, the fun has just begun. No, really, we're close. So we gotta get rid of this 1 over y, though. So we're going to multiply this side times y. And we'll put that up there because what do we know about y? Y is the original function. So we're going to multiply by x plus 3 squared, 2x minus 5 to the third, and 3x squared plus 1 to the fourth. Notice we have these terms down here. So we can cancel one of each of these terms. So we get a dy dx, or our f prime of x, equal to this numerator, 78, that's an 8, x to the third, minus 350x. I guess I probably should have put those in descending order, but I'm not going to go back and do that. You can if you want. X plus 3, or 2x minus 5, and 3 up to the second, and 3x squared plus 1 to the third. We could, if we want, and multiply all this out, but I'm not going to make you do that. We're going to leave it just like that, and that'll be our final answer. All right, so in example 4 here, we have basically the same thing. We have a function, but now we're dividing two things. So I'm going to again change this f of x to y. I'm going to take the natural log of both sides. This one's not as miserable as the last one there. So I'm going to go ahead and break this up as well. So if I have a well, just do this here, I guess. Natural log, I'm going to change these to a fractional exponent and change my x plus 2 to the 1/3 power. Remember, we take the exponent divided by the index to change it from a fraction or from a radical to a rational exponent. So we can go ahead and split this up. We have division. Division we're going to split up through subtraction, and we'll bring these exponents to the front. So I have the natural log of y equal to 1/2 the natural log of 2x minus 5 minus 1/3 the natural log of x plus 2. Now I can go ahead and find my derivative. So 1 over y dy dx is going to equal 1/2 of derivative of the function, which is 2 over 2x minus 5, minus 1/3 times derivative of x plus 2 is 1 over the original function, x plus 2. Clean this up just a little bit. My 1/2 and my 2, those are going to cancel. So 1 over y dy dx is going to equal 1 over 2x minus 5 minus 1 over 3 times x plus 2. Go and find my common denominator, which is again going to be smashing these denominators together. I'm going to put my 3 first, just make it look a little nicer. And then times my x plus 2. So the 1 here is going to get a 3 times an x plus 2. So it's going to get 3x plus 6 minus, I'm going to take my 1 here and multiply it to 2x minus 5. I'm going to be very careful with that minus sign because it's got to distribute to everything in here. So I'm going to take that 2x minus 5 and multiply it by negative 1. So I'm going to get a minus 2x and then plus 5. Cleaning up my numerator there, I get x plus 11 over my 3, 2x minus 5, and x plus 2. And again, that equals 1 over y dy dx. I'm going to multiply my y over, so I'm going to multiply this by y, again, putting that up there because I know that y equals 2x minus 5 to the 1/2 over x plus 2 to the 1/3. So I'm going to go ahead and put that in there, 2x minus 5 to the 1/2, and then x plus 2 to the 1/3. And now I can go ahead and clean up. So I have 2x minus 5, one on top, one on bottom, actually a half on top, one on the bottom. So I can cancel out a half of those. And on my x plus 2's, since they're both on the bottom, I can add those exponents. So I get x plus 11 over 3, 2x minus 5 to the 1/2, and then times my x plus 2, 1 plus 1/3 gives me 4/3, and that's my dy dx. And that's my final answer for my derivative. I have one last one. Remember this one? We've talked about this one a little bit. So we have x to the x plus 1. Remember how to find the derivative. How do we find that derivative? I'm going to go ahead and change again this to my y. I'm going to take the natural log of both sides. So natural log of y equals, if I take the natural log of this side, I can bring this exponent to the front. So I have x plus 1 natural log of x. Now I can go ahead and find the derivative of this. So I get 1 over y dy dx equal to, I have a product rule since I have two variables, in one variable in each part of two different things there. So I have x plus 1, derivative natural log of x is 1 over x, and to that we're going to add the natural log of x times the derivative of x plus 1, which is 1. I can go ahead and multiply my 1 over, or my y over if you want. So we get dy dx, that's going to equal, I have x plus 1 over x plus the natural log of x, and it's all going to be multiplied by that x to the x plus 1. Ta-da! Can we find a common denominator? Yes, we could find a common denominator. So we'd have x plus 1 plus x natural logs of x over x. And why would we do the common denominator there? Well, notice we do have a common base here, and that's an exponent of 1. So if I take x to the x plus 1 and divide it by x to the first, I'm going to subtract those exponents. So x plus 1 minus 1 gives us x, doesn't it? So we get x plus 1 plus x natural log of x all times x to the x. And that would be my derivative of that x to the x plus 1. So that gives you an idea of where we can use our implicit differentiation to make a miserable problem a little easier. And it also gives you an idea of how to find the second derivative with those natural logs. So if you have questions, let me know. Good luck, enjoy, and happy derivating.